Okay, proofs with perpendicular lines. So a lot of this section is going to be algebra review. Um, okay, so I'm going to start off with slope. So we use a lowercase m a lot of the time for slope. And slope describes how tilted a line is, right? What kind of tilt it has to it. You can describe it by the rise over the run, comparing how far from one point to another, how far up and down it goes versus how far left and right. And there's also a formula. You subtract your y coordinates in the numerator and your x coordinates in the denominator, like so. Okay. It's good to remember if you're reading this from left to right, that's going uphill. And when you've got a line that goes uphill, you're going to have a positive slope. It's just a nice way to check your answers, and if it's going downhill, it's going to be a negative slope. Okay, and I also want to take a second to talk about these two lines. One of them's vertical, one is horizontal, and let's talk about the slopes of those. So here's how I remember it, or at least how I teach it these days. So you can ski on this one, right? I'll show you. So there you are, right? You're skiing. See? It's cross-country skiing, I guess. There's your little poles, okay? This one you can't ski on, not so much. You could ski on it once, I suppose, but this would happen, right? It's a cliff, and then you'd end up down here, and yeah, not looking so good. Yeah. It's kind of a sad scene here. Ski over here and ski over there. Yeah, you wouldn't want to ski on that one, or that would happen. Okay, so this one does have a slope. It has a slope of 0. And this one does not have a slope because you can't ski on it, so no slope. Or sometimes you'll see that described as undefined slope. Okay, all right. And let's find the slope of a line that goes through these two ordered pairs. So you could graph this and kind of count the spaces up and to the right, but if you don't have a graph, I would just use the formula. So I'm going to call this x sub 1, y sub 1. It's the first x and the first y. And here's my second x and second y. And I'm just going to plug them into the formula up above, where I subtract the y's in the numerator and the x's in the denominator. And so I've got 5 minus 3 in the numerator and 4 minus 1 in the denominator. That gives me 2 over 3. Okay, and you want to reduce this. This one is already reduced, but say I ended up with 4/6, then I would reduce it to 2/3. Okay, and don't write it as a fraction or as a mixed fraction or a decimal. You want to leave it as a reduced improper fraction like that, because then we've got to compare. We've got the rise over the run. It makes it a lot easier for graphing. Okay, so you can go ahead and try this one if you like. You can pause it. I'm just going to work through it. So subtracting my y's in the numerator and my x's in the denominator. Just going about my way. What the? I've got a 0 in the denominator. Okay, and we can't divide by 0, right? You can't take $4 and put it in 0 piles. It's okay to take $0 and put it in 4 piles. You just put 0 in each pile, but you can't have a 0 in the denominator. So this is undefined. Okay. And actually, it makes sense if you were to graph these 2 points. If you had the point 2, 3, I'm just making a really quick sketch there. 2, 3 would be something like that. 2, 7 would be something like that. And the line that goes through those would actually be a vertical line, which has no slope. So it actually makes sense. It works out with what we talked about up here. Okay. All right. All right. So let's move on to slope-intercept form. I know you've seen this before, but it's back. So the m is the slope. The b is going to be the y-intercept. Okay, that is slope-intercept form. It's probably the easiest one to graph, I think. Well, point slope's pretty straightforward too. But okay, so here we've got a line in slope-intercept form. So my slope here is negative 2/3. Okay, and then here's my y-intercept, right? Okay, so when I'm graphing these, I always start with the y-intercept. So here's my y-axis, right? It's going to cross the y-axis at 1. So I know my line goes through that point. That's the y-intercept. Now I need to use the slope to get to another point on the line. So what I can do, I can use the slope, use directions to get from the first point that I already know to another point. Now the question here is, where should I put the negative? Does it go in the numerator? Or does it go in the denominator? Well, it doesn't really matter. You can choose, okay? But you want to put it one way or the other. If you just did up 2 to the right 3, then you'll end up with a positive slope. So you need to put that negative somewhere. So I'm thinking of rise over run. So if my rise is negative 2, I would go down 2 and then to the right 3. 1, 2, 3, which would put me right there, okay? Let's say I had chosen this one. Well, then my rise would be 2, and my run would be negative 3. So I'd be going 3 to the left. And I actually end up with the same line either way. There it is. And I was just doing that freehand. Should have used a ruler, but oh well. There it is. Okay, so there's our line. All right, let's move on to the next page. Okay, so now we're going to write an equation in slope-intercept form for a line through these 2 points. Okay, and I've got a game plan here. So here are the steps. We're going to start by finding the slope. Okay, so let's do that. I'm going to subtract my y, so I've got negative 5 minus negative 3. Watch that, got a double negative there, right? And then I've got 10 minus 2. Okay, so negative 5, that would be the same as negative 5 plus 3. And 10 minus 2 is 8. Okay, so I've got negative 2/8, which I can reduce. That would be negative 1/4. And again, it doesn't really matter where you put the negative. You can put it on top. You can put it in the middle if you want. But yeah, it makes no difference. Okay, and then next I'm going to substitute one of the xy pairs into y equals mx plus b. Okay, so let's do that. So I've got y equals mx plus b. Okay, I'm going to substitute one of these xy pairs. I'm just going to use this one because the numbers are smaller, but it doesn't matter. You could use either one. Okay, so I'm going to put in negative 3 for y. And I actually know the slope, so I'm going to substitute that in as well. So I guess I should have put that in one of the xy pairs and the slope in that I've already found. And then my x is 2. Okay? And now what I can do, I can solve this for b. I've only got one one variable in this equation now. Okay? So let's go ahead and work through this. So you can think of this as 2 over 1, right here. So I'd have negative 1 times 2 and 4 times 1, like that, you know. Okay, so now I've got negative 3 equals, let's reduce that, negative 1/2 plus b. And then I'm going to add 1/2 to both sides so that I can solve this for b. Okay, let me move up here. So b is going to equal negative 3 plus 1/2. Okay, so let's get a common denominator here. I can rewrite negative 3 as negative 6/2. Okay, and then the denominator will stay the same. On top, I've got negative 6 plus 1. The denominator stays the same. And there's my b value. Okay, and then the last step, I'm going to substitute the m and the b. Okay, so I know it's in the form y equals mx plus b. So my y is just y. But m is, where was the m? The m is negative 1/4. And the b was negative 5/2. So you could say plus negative 5 halves, but I'm just going to write that as minus 5 halves because that's the same thing, okay? And there is my solution, okay? So really you need to find two things in order to write your equation, and there they are. You need the slope and the y-intercept, okay? So you can go ahead and pause it and try the next one. Okay, I just did the whole next problem and then looked up and realized I did the whole thing off screen. So I had to print out a new one and I got to do it again. It's a hard life, but that's what I got. Okay, so I'm going to find the slope first, and I'm going to move the paper up so I don't have to redo this again. Okay, subtracting the y's in the numerator, and then the x's in the denominator. And I've got a double negative there, right? 6 minus negative 4. So I've got negative 10, and that would be the same as 6 plus 4. Okay, so my slope comes out to negative 1. Okay, so phase 1 complete. Now let's use y equals mx plus b. I'm going to substitute in one of the xy pairs. I'll use that first one. So I'm going to put in 3 for y. And I've also got the slope. Okay, and then the x was negative 4. Okay, I'll do the multiplication there. And then I'm going to subtract 4. Okay, and now I've got the two important pieces of information, and I can write my equation in slope-intercept form. So I'm just plugging in those two bits. Okay, now you could write negative 1x, but negative 1x is just negative x, and then minus 1, and there we go. Got the whole thing on screen. All right, I did it. Okay, so let's move on to point-slope form. So similar kind of deal here. We still have the m, which is the slope. This has a new feature. It has x sub 1, y sub 1, which is a through point. What I call a through point, and that just means that's going to be a point that the line goes through. Okay. So let's write an equation here. So we're going to need a point that this goes through. Hey, well, we've got two of them. We've got two of them given away for free here. Okay, so that's great. So we can use either one of these as x1, y1. It actually doesn't matter which one. I usually just use the first one. So I'm going to use this one. And I'll call that my second x and my second y. And then we're also going to need the slope. So let's go ahead and find the slope. So anytime you're writing an equation of a line, you're going to want a slope. So it's either given to you or they'll give you enough information to find it. So subtracting my y's and then subtracting my x's in the denominator. Check for that double negative. So that'd be 2 plus 3. So negative 6/5 is what I got for the slope. Okay. And now I'm already ready to start plugging all the bits in. Okay, so I need to plug in this, and this, and this, and I can do that. So my y sub 1 was 1. The slope was negative 6/5. X sub 1 was negative 3. So heads up here, I'm subtracting negative 3. So I wouldn't want to leave my final answer like that with a double negative. So since I don't feel like rewriting it, I'm just going to do that little trick. And then got my equation, okay? Let's say for whatever reason I wanted to put this in slope-intercept form. I could distribute the negative 6/5 and then add 1 to both sides, and it would be in slope-intercept form, okay? All right, there's a third form of a linear equation, which I'm not going to get into too much here, but I just want to throw it out there since we covered the other two. That's standard form. That's when you have your x term first, and then your y term, and then your constant, which just could be any number. So that's just an example of a linear equation in standard form. Not really going to do anything with it right now. Okay, all right, let's move on to the next page. So this is where we actually get to some new stuff. So the geometry book kind of assumes that everyone remembers linear equations, how to graph them, and how to write equations and so forth. But I wanted to go over it because I found that isn't always the case. All right, so we've got a couple of theorems here. The first one is called the linear pair perpendicular theorem. Okay, so I've got a little if-then statement here. So this says if we've got two lines that intersect like that, and two of the adjacent angles are congruent. So if those two are both congruent, well, let's think about this. If they're together, they would have to form 180 degrees, right? Because it's a linear pair. So that means they're going to be split evenly, that 180 degrees. So those would both have to be 90-degree angles, which really means we've got perpendicular lines, right? So if you've got two adjacent angles that are congruent like that, then you end up with perpendicular lines, and that's that theorem, okay? Next up, we've got the perpendicular transversal theorem. Okay, so this is a transversal, right? It's cutting across the other two lines, and I've got two parallel lines here, and my transversal is perpendicular, so you can see where they got the name from, the idea for the name, okay? And here's the deal. If you got they have to be parallel lines, and if your transversal is perpendicular to one of the parallel lines, then it's going to be perpendicular to the other one. Okay? And that's the whole idea there. Okay, that only works if the lines are parallel, but if they are, it works every time. Okay? And actually, you could do this with corresponding angles, right? Those two would be corresponding angles, which means that would have to be 90 degrees as well. Okay. All right, and then we've got the lines perpendicular to a transversal theorem. These three theorems for me are really difficult to memorize the names of them because they all sound really similar. It doesn't really matter that much to me personally that you memorize the names of these theorems. They won't show up in proofs very often. They will once in a while. It's more important to me that you understand the concepts and you get how to use them, okay? So, hey, we've got two 90-degree angles here. So that means both of those 90-degree angles are congruent to each other and they're in corresponding positions, right? So that means that my tracks are going to be parallel. So, you could have used the converse of corresponding angles to say the same thing, but now we can also do that with the lines perpendicular to a transversal theorem. Okay? All right. Now let's talk about finding the shortest distance from a point to a line. Okay, if we were teaching in person, I'd talk about, well, let's say I wanted to get to that wall over there, a wall on the other side of the room. I would go straight to it. Yeah, I could go to one of the corners, but I would go the shortest distance, which would be perpendicular to it. It'd be, it's going to be the perpendicular distance is always the shortest distance. Okay, so that is an important concept. So let me show you on this. Okay, so here I'll draw a little picture. Here's me. Here's the wall, and if I want to get to that wall, I want to go that way, right? I could go there and get to the wall, but it would take a longer time. It's a longer path. The shortest path is going to be the perpendicular path, okay? And that's illustrated on this next problem. We're going to find the distance from point A right here to line L, which is this bold line there, okay? So we've got three different paths in the picture, and you just have to be able to recognize that when it says the distance, it means the shortest distance. So the distance, yeah, you can make an argument it's any of those, but in a geometry book, the distance is going to be the shortest possible distance, and that's going to be the perpendicular one. So I'm only interested in AC. So these ones are just there for fun. They're just there to distract you. We don't need those at all. So really what we're going to do is find the length of this line segment then, okay? So I'm going to find the length of AC. I'm going to do that with the distance formula. From a couple of chapters ago, I promised you that it would never go away, and it's not. Okay, there it is. All right, so let's start plugging in the pieces. I'll call this x1, y1. And I'll call this x2, y2, but really it doesn't really matter which point's your first one and which one is your second one. All right, let's start plugging the pieces in. So 2 minus negative 3 for the x's. And I'm squaring that. And then for the y's, 1 minus 4. I'm going to square that. You got the double negative there, so 2 plus 3 is 5. And then 1 minus 4 is negative 3. And remember to do everything under the radical first. So I need to do this, simplify and add these pieces together before I take the square root. So then I've got 25 plus 9. And I've got root 34. Okay. And it says round to the nearest tenth here, so that's what I'm going to do. I'm just going to put it in a calculator. I know it's going to be a little less than 6 because root 36 would be 6. And if you put it in a calculator, it'll be approximately 5.8. So there is the distance from the point to the line. It's the length of that orange segment there. And that is it. See you next time.